Well, this is the last week of your course, 3-month course, and we are beginning our 12th week. And I will talk on a topic which never should happen if you are doing condition based monitoring correctly. That is failure analysis. Okay, we have been doctors so far, where we have diagnosed the fault, sometimes given good remedies to cure the fault or the machine, but despite our best maintenance efforts, machines may fail, machines will fail, because no system is perfect. And if you believe in the thermodynamics second law, there are reasons why things will fail. Okay, no system is perfect. But question is, do we learn from the failure? And what does the failure, what new information does the failure give us? And that is very important. Can we learn from our mistakes in design, in maintenance, in manufacturing, in material selection, so that the component has failed? Okay. So, as you see, I tell the areas of material selection, design, manufacturing, maintenance in that sequence. So, most important comes at the location of material selection. So, we leave it to the designers who would have done a good design selecting the optimum material, but sometimes I have seen in many instances we have imported machines in steel plants where rolling mills have failed because the designers would have specified a particular material, but the manufacturer may be, for some unknown reasons, used a different material of an inferior quality, maybe not do a proper heat treatment process, and in the process we have just bought a new machine despite our best CBM technologies which we have implemented in it, there are failures. So, we will go to the step by step reasons why failures occur, and then if a failure has occurred, how to do a forensic examination or what is known as the post-mortem of a dead human being. So, we will become a forensic doctors towards the end of this class. Okay. So, well, materials will fail. Okay. Materials will fail because, and looking at the failure, we can know what is predominant the reason of failure. A ductile material, if it would have failed, it would make a cup and cone like a form. So, looking at the failed component, and those of you who are students, you would have seen when you do a uniaxial test of a mild steel specimen in an UTM, universal testing machine, you will come across such cup cone type failure. Okay. And this material is mild steel, which is ductile. But in the brittle, their failure is sudden, okay, and then you will have a lot of shiny spots on the surface. So, looking at this surface, we get some clue as to what kind of failure is happening. But I will see in machineries, many of the shafts are subjected to fatigue load, and because there could be a surface defect, surface crack, surface roughness, a fracture would have occurred and they would proceed like this and leave such beach marks, and finally, the structure would have come to an area would have been reduced significantly, that the system or the shaft is not able to take the load anymore, and then there will be a sudden failure. So, looking at the fracture surfaces, one gets a clue as to why it has failed and how it has failed. Of course, there are other methods. Looking at this fracture surface or doing the analysis on the fractured component, we can talk about how the failure has occurred. That is what is the importance. But let us see what happens in some of these operations which perhaps goes unnoticed or which lands up in the final design or final component because our design or our processes were not robust, not having robust, foolproof systems in place. So, many of the industries where we have ISO certification, documentation is very important, so that such errors do not propagate and every operation which we do are properly documented and we follow that sequence. And if still mistakes are happening, we can take care of it. So, some of the problems which occur, cracks due to abusive machining, I mean we are going at a very high speed or depth of cut, tool chatter or cracking due to speeds and feeds, microstructural damage due to dull tool, grinding burn, electrical discharge machining, recast layer cracking, electrochemical machining, intergranular attack, residual cracking due to overheating. So, you see these are processes where a CBM, it is beyond a condition based maintenance engineer's control, but had the manufacturing operations been done correctly and these did not happen, our machine would have had a better life. So, one has to be careful about this. Similarly, in the other metalworking processes, cracking, tears or necking due to forming deep drawing, laps due to thread rolling or spinning, tool marks and scratches from forming, surface tears due to poor surface preparation prior to working, residual stress cracking due to flow forming, Luder line due to forming strain rate, microstructural damage due to shearing, blanking, piercing, overheating damage during spring winding, laps and cracks due to short pinning, stress corrosion cracking due to use of improper dye lubricants. Again, in many of the metalworking processes, these kind of problems do happen, but sometimes they get overlooked and we may be doing we would have bought a new machine and we are doing very religiously, we are doing CBM, but this problem will occur because we have not taken into care the problems which has occurred during the manufacturing operations. So, one has to be careful that the proper manufacturing procedures are followed. Well, it is not in the CBM engineer's control, okay, but a good machine manufacturer ensures that these things do not happen. Similarly, during heat treatment, the time TT, time temperature okay, how quickly we bring down the temperature as a function of time helps developing microstructures, whether martensite is formed, perlite is formed, it all depends on the cooling rate. Okay. So, the heat treatment processes control all this, grain growth, incomplete phase transformations, quenching cracks, decarburization, untempered martensite, temper embrittlement and similar embrittlement conditions, inadequate precipitation, sensitized microstructure, inhomogeneities in microstructure, loss of properties due to overheating during post-plating bake. So, the heat treatment plays a significant role in the microstructure formation. Okay. So, that is why and these are all very set manufacturing process. I underline the word, they are well defined manufacturing process. Well, sometimes because of a production demand, some of these operations or safeguards may be overlooked. So, that is why in a plant the documentation and quality checks at every stage is very important, and we have to ensure that only through proper go, no go tests. I was if you refer to one of the classes on dye penetrant test, I talked about using dye penetrant to find out whether the cylinder block which has been casted has a surface crack. Imagine if the surface crack went unnoticed and we manufactured a nice engine out of this cylinder block, and then we put it in a vehicle, and then the customer complains that suddenly he is losing power and the engine suddenly the coolant oozed out of the engine and the engine seized. So, one stage where we overlooked a crack in the cylinder casting because the dye penetrant test quality checks was not done, we will end up with a problem downstream. So, these are to be avoided as good designers or manufacturers. Another important area you will see in a lot of engineering applications, welding is done. Okay. And of course, I had told you when we do NDT, ultrasonic checks or sometimes even radiography tests are done, particularly in nuclear reactors, nuclear applications. The checks are very stringent, because improper welding will lead to all these problems: lack of fusion, brittle crack in heat affected zone, sensitized heat affected zone, residual stress cracking, slag inclusions, cratering of fusion zone at end point, filler metal contour out of specification, hot cracking, cracking at low exposure temperatures, hydrogen embrittlement due to moisture contamination. So, these are all issues which happen in your welding. So, again when we weld a structure, so if I put a weldment here, so some of the zones they will be heat affected because of the high temperature. Okay. So, there will be residual stress build up, and then on top of it, if it is subjected to residual fatigue loading, there will be quick failure. I have seen in my book, you can see a failure analysis of a bend pulley in a conveyor system. Because if you will see in a conveyor system which is rotating between a header pulley and tail pulley, during the return there is a onto this certain weights are given. This is the bend pulley. These weights are given to maintain tension in the conveyor belt. Excuse my typos and spelling mistakes, that is because in the flow I want to rather concentrate on the topic here. So, this bend pulley failed, and you will see in my book the details of which you can find in the website. Okay. This failed, and we realized after doing a failure analysis, it was improper heat treatment done after welding of the pulley. Okay. The pulley is nothing but a big cylinder, okay, onto which a shaft is welded. Okay. Of course, these are again welded. So, there is a lot of failure in these weldment areas, okay. And this on top of it, this belt goes over it, and these are made to rotate. Okay. So, HSZ and improper heat treatment was the reason, and this was discovered by doing a chemical analysis of the component, failed component. And again, in many of the cleaning finishing operations, corrosion due to inadequate cleaning prior to painting, intergranular attack or hydrogen embrittlement due to acid cleaning, hydrogen embrittlement due to plating, stress corrosion from caustic autoclave. So, this hydrogen embrittlement creates a lot of problems. Again, failures can occur because of assembly at factory installation site, misalignment, missing wrong parts, improper startup, inappropriate fastening system, improper torque, improper tools, inappropriate modification, inadequate surface preparation. So, all these things add up to the failure of the component. Okay. Some of the inspection techniques, arc burn due to magnetic particle inspection, intergranular attack or hydrogen embrittlement due to macrotech, fatigue or quench crack from steel stamp mark. So, all this could lead. Okay. Now, once a failure has occurred, what do we do? Despite, so these were the reasons by which failure occurred. So, whenever a failure has occurred, I would say this is the procedure which is to be done. Okay. It is just like a crime scene. Okay. Do not disturb the failed site. First step, take a lot of photographic documentations. Today, of course, nowadays people are also doing videography, etc. But good photograph with high resolution camera is good enough to show where the failed components have fallen or what is the condition of the surface, and then immediately some of the components which are failed, many of the non-destructive testing can be done. So, what are the non-destructive testing we can do in ultrasonics? If there are small fragments, we can do micro hardness measurement. For some machines, we can measure the micro hardness and also the tensile strength. So, whether the component had the desired strength, many times we have seen that a material of inferior quality has been done. Some components we can have an X-rays, and the material verification becomes very, very important in terms of both at the microscopic level that we do through an metallurgical analysis like an XRD, by an X-ray to find out chemical composition, or we do spectroscopy analysis. But these failed components which are lying around, so we can take a sample, but many times when we take a sample, do not use any powered electric saws. So, there should be because when you take a sample, the heat during the cutting operation, heat during cutting operations must not change the microstructure. Because when we examine the failed component under optical microscopy, either through a scanning electron microscope to see the grain structure, any extra heat which has been generated when preparing the sample is going to damage this component. Okay. And then all the mechanical properties, whatever we can measure, like yield point or ultimate or hardness, impact strength. Okay. But since the sample is very, very small, we need to have nowadays we have nano indenters, wherein we can find the hardness as a function of depth of penetration, and during the unloading or the retraction we can find out the Young's modulus. So, today a lot of such techniques and machines are used to find out all these properties, but then question is, from a site these components need to be nicely documented, packed and transported to the failure analysis lab. So, sometimes the CBM engineer may not be well versed with the technique, but at least he can do this, and then This will go to a trained metallurgist who will do such analysis and maybe from the grain structure tell you what was the grain structure, from the SEM composition, from the XRD analysis, from the spectroscopy analysis, tell you the composition of the material, the grain boundaries, the grain structures, the process of heat treatment, etc., and how this has happened. And then of course, you have to write a report. So, some of the material selection which we depends on these, we can measure some of these properties after in the failed component: tensile strength, yield strength, modulus of elasticity, ductility, fatigue strength, fracture toughness, hardness, shear strength, machinability. So, all these components or all these factors or parameters let us know the behavior of the mechanical component which has been put in that machine. Okay. And of course, these are some of the other properties, so designers would have done that. So, there is always failures occur because there is a disconnect between the materials vendor supplier, vendor for the material supplier, the designer, the manufacturer, the machine installer. All these problems happen. So, somewhere somebody has done a mistake and it propagates downstream because we do not have robust quality control mechanisms in place and failures can occur. So, in the failure investigation procedure, you have to document the evidence, service conditions, materials handling, storage and identification, lot of talking to the operators, the engineers at site, and lot of testing is to be done. Okay. Thank you.